y2 from y1 and so on, then y2 with respect to y0 can be written as 1 plus lambda h square. Similarly, if you were to write in terms of yn, in terms of 0, 0, 0, y2 from y1 and so on, then y2 with respect to y0 can be written as 1 plus lambda h square. Similarly, if you were to write in terms of yn, in terms of y0, so let's say this is the initial profile that is given, initial value, then it is going to be 1 plus lambda h to the power n times y0. Okay, then we said lambda can in general be complex, right? That means lambda can be decomposed as lambda real plus lambda imaginary. So we have lambda real plus I times lambda imaginary. That's what we said. Now we again looked at several things. So we said the entire plane that is to the left of origin, that is essentially entire range of lambda r less than or equal to 0 has a solution, right, as an analytical solution, whereas we said when lambda r is less than or equal to 0, if you have only then whereas for the explicit Euler method, we have proved yesterday that essentially this is a circle which is going from -2, -1, 0. So it is centered at -1 and it is a circle. And only in this region is where the stability region for explicit Euler method. Okay, this is the stability region for explicit Euler method, and we have plotted this on lambda real, lambda imaginary, whereas this one we have plotted on lambda real times h, and this is lambda imaginary times h. Okay, that means if you have a problem where you want to solve y prime equals lambda y, lambda can be some value. Now that means although you can obtain for all real magnitude of this is less than 0, and then it can have any other imaginary value, imaginary component. If you want to solve it using explicit Euler method, we said you would choose the time step or the time step h in such a way that lambda times h happens to fall inside the circle. Okay, so that is the idea here. That means we have to adjust h such that lambda h falls within the circle. Okay. Now we also said, okay, if you have purely real values of lambda, that means lambda I is equal to 0. That means for purely real values of lambda, that means lambda r is less than or equal to 0, because lambda r can never be greater than 0. You will not get any physical problems where things will grow indefinitely, right? So then lambda r is less than or equal to 0. If that is the case, we can say that essentially we are, because lambda r is the only thing that is available, we are on the x-axis, right? Essentially, we are on the x-axis. So that means we can go from as along this shaded red region. So that means lambda r times h at max can be less than or equal to 2, right? That means we should choose h to be less than or equal to 2 by modulus of lambda r. So that is the h value we should choose. That means h can be at max 2 by lambda r, right? So that is the conditional stability that we have. So conditional stability of the explicit Euler method, okay, given by h equals or h less than or equal to 2 divided by modulus of lambda r, right? That's what we have. So we cannot take any value higher than this thing, because that will lead to divergence. Okay, fine. So that is what we have looked at yesterday. Now let us try to wrap this up. I think towards the end I made a statement which is incorrect. So I said, let me look at purely real values of lambda. That means lambda r is only there, like lambda r is non-zero, and then lambda I is equal to 0. And then let us consider the case where the solution is unstable. Okay. If the solution is unstable and we have purely real values of lambda, then what we have is we have 1 plus lambda h modulus is greater than 1, right? That means this is greater than 1, and we say that this is basically only real values. That means we have 1 plus lambda r h is greater than 1. So, and we say that although lambda r is negative, right? If this happens to be greater than 1, then what we have is basically this entire quantity, right? For it to be greater than 1, we say that essentially 1 plus lambda r h has negative value, right? With magnitude greater than 1, right? So this is only possible when this has a negative value that is greater than 1, that its magnitude is greater than 1, right? So if this is the case, what will happen? That means 1 plus lambda h, lambda r h has a negative value. For example, let us say I take h equals 0.5. I take lambda r equals, let us say 6 or minus 6, right? We are in the negative this thing. So let us take minus 6. Then this quantity is going to be 1 minus 6 by 2, right? This is going to be minus 2, right? So this is greater than 1 in magnitude. So in magnitude, this is greater than 1. But then the value of 1 plus lambda r h itself is negative, right? So 1 plus lambda r h is negative. In this case, it is minus 2. But when you take its absolute value, that is greater than 1, okay? And when you have such a case, okay, so I'm making up a case like this. That means the h we have taken is actually not sufficient. Ideally, we should have taken h to be less than or equal to 2 by modulus of this thing. That means 2 by modulus equal to 1 by 3. That means we should not have taken h to be should have been taken as 0.333, right? But I have taken h to be equal to 0.5, which is greater than this value. Okay, so that's why we see that. I mean, that's why we say that the solution is unstable, right? Because the magnitude has come out to be greater than 1. If I had taken it to be 1 by 3, then things would have been below 1 and it would have kind of converged. Okay, then what is the point we're trying to say? So when you see that, let's say the solution is unstable when 1 plus lambda h is modulus is greater than 1 and lambda is a real value and it is negative, then what will happen? Then essentially 1 plus lambda h is negative. So what does it mean? It means that when I look at the solution, so you have yn plus 1 equals sigma, or I mean, we have 1 plus lambda h, right? So we have 1 plus lambda h times yn, right? That is the explicit Euler method applied to the model problem. Okay, then what will happen to yn? Yn, we wrote this as 1 plus lambda h to the power n y0. Okay, when let us say 1 plus lambda h is negative, what will happen to 1 plus lambda h n, right? What will happen is that when n equals 1, 3, 5, and so on, for the odd values, this yn will come out to be negative, right? Yn will come out to be negative because this is a minus value raised to an odd power. When n equals 2, 4, 6, 8, and so on, then yn will come out to be a positive value. Okay, that means your solution is going to go from so you are given y0, then y1 value will be negative, y2 will be positive, y3 will be negative, y4 will be positive, and so on. That means your solution is going to grow like that, right? So it's going to flip from positive to negative after every h value. So that means it's going to show oscillatory behavior. Oscillatory behavior, and such an oscillatory behavior is an indication of divergence. Okay, so we should be careful. So it means if there is an oscillator behavior that is being seen, then we know that essentially the solution is eventually going to diverge. Okay, that means this kind of an not just an oscillator behavior. The behavior is ideally supposed to be damping, right? Because you have lambda r equals -6, so it should be damping. But you see that it is an oscillator behavior and it is a growing oscillator behavior, right? Because lambda 1 plus lambda h is greater than 1. So you're going to see that this is growing. Okay, so this is growing. So you see a growing oscillatory behavior in the solution is an indicator of divergence. That means this indicates that either the method is unstable or the for all values of h, or it is unstable for the value of h we have chosen. So we should go back and reduce the h value, okay, so that the method becomes stable. Fine. Okay, so then let us see if I can. So ideally, we should be able to kind of write a code and do this thing, but I'm going to just give you an idea here, so you can go back and write a code. Let us take an example problem for the explicit Euler method. Okay, so let us say the example problem is y prime plus 0.5 y equal to 0. Okay, that means this can be written as y prime equals minus 1/2 y, right, or minus 0.5 y. Let us say y of 0 equals 1, and we want to take different h values. Okay, and then we want to integrate this to 0 less than t less than 20. Okay, so t equal to 0 is given as 1, y prime plus 0.5 is what is given. That means this is a real value. So our lambda r equals minus 0.5, that is what is given. So we know that the exact solution to this problem is basically y prime by y. That means you're going to get e to the power lambda t is the exact solution. That means e to the power minus 0.5 t, right? So this is the exact solution. Y equals minus 0.5 t. That is the exact solution. That means if you were to plot this in a you calculate this using MATLAB or something, then you would see that essentially the exact solution is this is has the value of 1, that is at t equal to 0, your y is a value of 1, y of 0 equals 1, and then it's going to decay as exponentially as you go like this. So this is the exact solution we will obtain. Let us say this is at the value of t equals 20. Okay, so this is at 0. Fine. Now, for this particular problem, what is the maximum h we can take? So h should be less than or equal to 2 by modulus of lambda r. That means less than or equal to 2 by modulus of minus 1/2. That means h should be less than or equal to 4, right? So if I take any values less than 4, then my explicit Euler method is going to give me converged values. Let us say I take a value of h equals 1. Okay, if I take a value of h equals 1, then I'm going to get, then my solution is going to look like very close to this one. So I'm going to get a solution that is something like this. So this is the solution for h equals 1. Okay, now let us say instead of taking a value that is consistent with the stability requirements of the explicit Euler method, I take a value of h equals slightly greater than 4. Let me take a value of 4.2. So when you take 4.2, what will happen is that your stability is not respected. So as a result, your solution will look like essentially like what we have discussed. Okay, so it's going to diverge. So it's going to oscillate. So I should have actually drawn this okay, different color. Okay, so your solution is going to oscillate. So you're going to see something here, because we have seen that this is 1 plus lambda h is now changing its sign, right? It is negative. So you're going to see something like this. Okay, so essentially it's going to ideally these should pass through this intus. Okay, what I have drawn. Okay, so it should go through. So essentially this is the diverging solution you will see. Okay, so which means that the times that you have taken for numerical integration is not correct. It is not following the stability criteria as such. Okay, if possible, yeah. So that is what about the explicit Euler method. Okay, any questions so far on what we discussed? So I think yesterday I made a kind of a different comment that was incorrect towards the end of the class. So you can correct it, that we are looking at an unstable solution for lambda r less than 0. Okay, and then purely lambda r values, no lambda I, purely real lambda values. Okay, Any questions so far on this, what we are trying to learn about the stability of the explicit Euler method? Okay, if not, I'll move on to the implicit Euler method. And please feel free to ask me any questions anytime. Okay, let's look at the implicit Euler method. Okay, so in the implicit Euler method, we said our yn plus 1 equals yn plus h times f of tn plus 1 comma yn plus 1, right? This is what we said. We're going to evaluate the function at the next time level and the next solution, right? The dependent value also. That means at tn plus 1 and yn plus 1. So in general, implicit methods are more computationally expensive, more in general are more computationally expensive. This is because in general f is a nonlinear function, and then solution of nonlinear functions requires you to solve either use an iterative method, right, or essentially use some kind of an iteration so that you would basically solve for the nonlinear part. But then we have seen that you can actually linearize the nonlinear function, linearize the function f and then solve. So that is possible. Even then, the computational cost is expensive for somewhat expensive for the implicit Euler method when compared to the explicit Euler method. However, this additional cost comes at the benefit of stability. So implicit Euler methods are far more stable. In fact, we will see that implicit Euler method is unconditionally stable than the explicit methods. Okay, so these are
Professor,
yeah.
In the last class, you have taught us that this implicit Euler's method is computationally more expensive than explicit because we have to use TDMA for getting the n+1 coefficient, and then backwards calculation has to be done that way, right, sir?
Correct. No, so
However,
that was
yeah.
So that was in the context of the PD, where we have done dou u by dou t equals alpha dou square u by dou x square. In the context of
logic
the
remains same over here also.
Yeah, it is pretty much the same logic, because that was more complicated in the basics of finite difference method. But here we are actually looking at just an ordinary differential equation. So you will not have to form a TDMA in this case. However, you will get a function in terms of yn plus 1. So you have to solve for a nonlinear algebraic equation at every delta t. Okay, that means at every step, we need to solve for solution of a nonlinear algebraic equation, which is the second chapter of what we have seen, because this will be primarily in terms of some function of yn plus 1 equal to 0, right? That is how you can write this thing, right? Once you discretize, once you bring all the yn plus 1 terms to one side, you could write this as some function of yn plus 1 equal to 0, which is basically some nonlinear function. Okay. Yeah.
Okay, sir. Noted, sir. Okay. Thank you.
Okay. So, but then we have also seen that this is you can linearize the nonlinear function, and then so that you can avoid the iterations. That is possible. But that is also going to be slightly more expensive than the explicit method, where you just substitute and then calculate. Okay. But then as we see, the implicit methods offers much more stability characteristics, better stability characteristics than the explicit methods. Okay, fine. So then if we were to apply the model problem that we have developed and then discretize it with an implicit method, then how does it look like? So essentially the model problem we have developed is y prime equals dy by dt equals lambda y. So again, this is the same model problem. Now I want to write what is the implicit Euler discretization for this thing. This is going to be yn plus 1 equals yn plus h times f of y comma t, that is going to be lambda times yn plus 1, right? Because this is going to be at tn plus 1 and yn plus 1, and right hand side doesn't contain anything related to tn plus 1. It is only in terms of y. So it will be h times lambda times yn plus 1. That means if I were to bring all the terms group the terms, then yn plus 1 minus lambda h yn plus 1 equals yn. That means yn plus 1 times 1 minus lambda h equals yn, or we can write yn plus 1 equals 1 by 1 minus lambda h times yn. Okay, so let us call this as your sigma. Then your yn plus 1 equals sigma times yn. Just like we have done it for the explicit Euler method, we can write yn equals sigma to the power n times y0. Okay, so this is exactly the same. Instead of going from n to n plus 1, if I have to go from 0 to n, then this basically factor will get multiplied, right? Because y1 is in terms of y0, y2 will get one more factor and within a multiplication and so on. Okay, that means where my sigma equals 1 minus 1 by lambda h. Okay, so this is the value I have. Now again, for so what we said was for stability, right? For stability, we want the modulus of sigma to be less than or equal to 1. That means 1 by 1 minus lambda h modulus to be less than or equal to 1. That's what we want. But in general, we said lambda can be complex. So lambda can be lambda real plus I times lambda I. Okay, if that is the case, basically what we have is we have 1 by 1 minus lambda RH minus I times lambda IH to be less than or equal to 1. Okay, now let us look at this left hand side thing. What is this quantity? So this quantity is basically a complex number, and a complex number which is 1 minus lambda RH minus I times lambda IH in general can be written as amplitude times a phase, right? We can write this as a times e power I theta. What is a? A is the magnitude of this, right? So this is nothing but essentially magnitude is so where a equals square root of real square plus imaginary square. That means 1 minus lambda RH whole square, and then I have plus lambda IH whole square, right? So that is what I have. Okay, okay, because this is going to be minus I square. So this is basically I square is minus 1, and then you get a minus 1. So this is what you would get for amplitude, and then your theta is going to be tan inverse of imaginary value divided by the real value. That means you're going to get lambda IH minus lambda IH divided by 1 minus lambda RH, right? That is what we would get. Okay, so what is this quantity? So this quantity is going to be, we got, is it 1 minus? Yeah, this is correct. Okay, this is correct. Okay, so this is your theta. That is basically imaginary part divided by the real part. That is your theta value. Okay. Okay, so if this is the case, then I can write this essentially as 1 divided by a to the power a into e to the power I theta, right? That means this can be written as e to the power minus I theta divided by a. Okay, and then we are looking at modulus of this to be less than or equal to 1. Okay, so I brought this e power I theta to the numerator, which became e power minus I theta divided by a. Okay, now what is this quantity? When will this quantity be greater than 1, or when will this quantity be less than 1? Okay, e power minus I theta, we said this quantity has always a magnitude, or the maximum or minimum value it can take is 1, right? Because this is cosine I theta minus I sin I theta. So the maximum value it can take is just 1. And what about a? A is in the denominator. So what about 1 by a? 1 by a is nothing but 1 by this quantity. Okay, that means 1 by square root of 1 minus lambda RH whole square plus lambda IH whole square. Okay, so we are only interested in problems for which lambda r is less than or equal to 0. We said physically possible problems have lambda r less than or equal to 0. So as a result, lambda r times h is negative. That means 1 minus this is always positive, and it is greater than 1, right? Because lambda r itself is negative. When you multiply that negative with this minus, it is positive, and that quantity is greater than 1. Okay, and then there is some quantity here which is again positive because you're taking a square of that. That means this quantity in the denominator is always greater than 1. Right? It is always positive and greater than 1. When you have 1 divided by something that is positive and greater than 1, this is always going to be less than or equal to 1, right? In fact, always going to be less than 1. That means for all values of lambda r, for all values of lambda r, and for all values of, for all negative values of lambda r, and then for any value of lambda IH, the implicit Euler method is always stable, right? This is always stable. That means implicit Euler method is unconditionally stable. Okay. That means you can take larger delta t than what you have taken for explicit Euler method. But then we realize that and it's similar to in the context of the PDEs, stability doesn't mean accuracy. Okay. That means you may be able to take larger H values, but then the solution may not be accurate. Okay. So what does that mean? That means that even if you take larger values of delta t or H, you will get a solution, but that solution is not going to diverge, right? It's not going to blow up. You are going to get some solution, but that solution doesn't look like, that means you're not going to get infinite values, infinite as your solution for the problem, but you're going to get some value, but it is not going to be correct. Okay. So let us try to look at this thing with the same example problem we have done. So before for the explicit Euler. So let us look at an example problem. And let us try to take pretty much the same value. So we have y prime plus 0.5, 0.5y equals 0. And then we say that y value at t equals 0 equals 1. And then we want to take time going from 0 to 20. Okay. Then let us try to solve this again. This is time. This is y. And then the exact solution is basically goes from 1.0, it decays as e to the power minus 0.5t. Okay, it decays as minus 0.5t. Then let us say if I take time step of 1, okay, then that's going to basically go very close to the exact solution. So the time step of 1 might go something like this. Okay, I'm just drawing it here. So this is h equals 1. Let us say now I take h equals, similar to the previous case, I take h equals 4.2. H equals 4.2 might actually look like, it is greater than the stability requirement what we had before, but it might look like something like that. Okay. So this could be the value for h equals 4.2. But you see that things have not diverged like in the case of explicit Euler method. But then we see that this is also not exactly correct because this is not accurate. Okay. As a result, because it is not matching with this thing. So that means from the stability point of view, we want to take as large delta t as possible, right? Because it is unconditionally stable. Because a larger delta t, so from the stability viewpoint, we would like to take and we would like to take delta t as large as possible. Okay. However, the solution may not be accurate. Okay. That means we want to keep the solution as small as possible from the accuracy point of view, but then we would like to keep delta t as large as possible from the stability point of view, because a larger delta t means that we need fewer steps to reach the final time, right? That means if I take a larger delta t, I can reach this t of 20 in a fewer steps. That means if I take fewer steps, I'm actually doing lesser number of computations. So my solution is going to be obtained quickly, right? But if I take a smaller and smaller delta t to get to time of 20, I need to take much more steps, which will basically consume time, right? For example, if instead of taking delta t equals, if I take delta t equals 1, in 20 time steps, I can solve this problem. But if I take delta t equals 1e minus 3 or something, then I would need 20,000 steps to go to the final time, which is computationally more expensive. Okay, that means from the stability point of view, we try to take as large as delta t as possible. However, we are restricted by the accuracy limits. Okay, so as a result, when we want a solution to be accurate, we cannot take a very large delta t. Okay, so that is the idea that we get from the implicit Euler method. Okay, okay. Let us move on to the numerical accuracy that we have learned before, but then we want to look at a slightly numerical accuracy in a slightly different way. So let us look at numerical accuracy. Kind of revisited. Okay. We talked about the model problem, right? The model problem was y prime equals lambda y. Okay, so that is the model problem, and we're going to deal with, let us say, lambda equals, let us say we have a purely okay, so essentially the exact solution to this problem is e to the power lambda t, right? That is the exact solution. Y equals e power lambda t. This can also be written as y equals e to the power lambda. T can be written as n times the delta t, right? Which is nothing but n times h. Okay, this can be written as lambda times n times h. That can, or y equals e to the power lambda t times y naught is the exact solution. Okay, times y naught. This is going to be e to the power lambda h to the power n times y naught. Okay, so that means the exact solution is given as y exact is equal to e to the power lambda h times n times y naught. Okay, we realize that again here lambda r is less than or equal to 0, and then there can be any value of lambda I, right? That's what we have. But when we look at the explicit Euler method, we have written y equal to sigma n times y naught, right? That's what we have written, where our sigma in the explicit Euler method was 1 plus lambda h. Okay, I think you can recall, just now we have done it. So this is equal to 1 plus lambda h. Now, if you go back to the previous classes, we have compared in the context of modified wave number. We compared the k with modified k, right? Or k prime, we liked it. And then we said, okay, the solution is not accurate in this region and it is accurate in the other region and so on, right? So essentially, we can comment on the accuracy. We can comment or obtain, okay, obtain the accuracy of the method. By comparing the numerical solution with the exact solution. Okay, by comparing the numerical solution with the exact solution, we can comment on the accuracy, right? This is what we have done before in the context of modified wave number. So I'm going to do the same thing here. So what does e power lambda h look like, and what is 1 plus lambda h? So if I compare, that means I want to compare sigma, which is coming from the numerical method. I want to compare sigma with e to the power lambda h. Okay, so that is what I have here. That means this is also e to the power lambda h, and this is sigma n. So I want to compare this sigma with this e power lambda h, because one is coming from the exact solution, the other one is coming from the numerical solution. Then this is we are doing to allow us to compare the accuracy. Okay, if that is the case, I want to compare sigma e to the power lambda h for small values of lambda h can be written as from the expansion of e power x equals 1 plus x squared by 2 factorial plus x cubed by 3 factorial and so on. We can write this as 1 plus lambda h plus lambda square h squared by 2 plus lambda cube h cubed by 6 and so on. Okay. Whereas sigma for the explicit Euler method, we have obtained as 1 plus lambda h, right? Now you see kind of a very good comparison. The explicit Euler method is only modeling this thing to first two terms of the expansion, right? It only has the first two terms. The remaining terms it doesn't have, right? The remaining terms it doesn't has. So it is only matching up to 1 plus lambda h. That means it is basically has order h square as the accuracy, right? This is what we have already seen. I mean, we have not done in this way, but we said because using Taylor series expansion, we are including only the first term or first two terms. So first term, so that's why it is as an order of accuracy of h square. Okay, again, this order of accuracy of h square is a local accuracy because this is per step, right? That means if you do n steps, then this order of h square is going to degrade to order h, right? So that means it has an order of accuracy of order h square locally per step and has first order accuracy globally. Okay, fine. So then what we say is that now from now on, we will also say, okay, then let's look at the implicit Euler method. Implicit Euler method, again, we wrote y at the n, which is the solution at the end point, n step equal to sigma to the power n y0. But in the case of implicit Euler, our sigma was equal to 1 by 1 minus lambda h, right? If you go back. So 1 by 1 minus lambda h is again can be expanded if you have small values of x, then 1 by 1 minus x can be expanded as 1 plus x square plus x cube plus and so on. Okay, so that is the expansion. That means I can write my sigma for the implicit Euler method as 1 by 1 minus lambda h can be written as 1 plus lambda h plus lambda square h square plus lambda cube h cube and so on. Okay, as we can see again in this case, 1 plus lambda h is 1 plus lambda h is there in the numerical solution as well as in the exact solution, whereas it is whereas the moment you go to the remaining terms from lambda square h square by 2 onwards, it doesn't match. Okay, it has a term, but it is still lambda square h square instead of lambda square h square by 2. Okay, so as a result, it doesn't match. So then what we can say is that the implicit Euler method is also first order accurate globally, right? So the implicit Euler, this we have already seen. Euler is also first order accurate globally. Okay, that's what we can say. Now, from now on, instead of saying what is the term that is being truncated as the local order of accuracy, we can say if the terms in sigma and the terms in e to the power lambda h match to lambda power alpha h power alpha by alpha factorial. Okay, if they match up to and including h power alpha lambda power alpha by alpha factorial, then we can say that a particular method has order h power alpha as the accuracy. Okay, so instead of saying that it is only matching up to lambda h, so if it is matching up to lambda h, it has an order of accuracy of h. Okay, an order of accuracy of h if it is matching up to that term, right? So that's what we can say. If it is matching up to h square alpha square h square lambda square by 2 factorial, then we say that it is globally second order accurate. Otherwise, it is globally first order accurate. Okay, so that is what we can say. All right, and then we can now look at so many a times, although this order of accuracy is useful, it is not kind of sufficient. We want to look at the order of accuracy from a slightly different perspective for certain problems. So for certain problems, we are interested in not only in the how the method is accurate in terms of amplitude, we are also interested in knowing how the method is accurate in terms of its phase. Okay, so there are certain problems for which there are oscillatory solutions. Okay. For example, if you take a spring mass system, then the solution is going to be oscillatory. Similarly, if you take a vibrating string or something, the solution is going to be oscillatory. So for all these oscillatory problems, let us consider that the real value is 0. Okay, the real value of the lambda is 0. And then let us say there is only imaginary value that is not equal to 0. That means we are looking at a problem which is y prime equals lambda y, in which case lambda r is 0 and then lambda I is non-zero. Let us call this lambda I as some omega I. That means we have 0 plus I times omega times y. That means I have I omega y is the right hand side. Okay, so I have only purely imaginary lambda. That means we are looking at purely imaginary lambda. Now this is very typical of problems like, as I said, like the spring mass damper systems or spring mass system and any other oscillatory problems. Okay, they'll have only purely oscillatory lambda. Okay, if it is y prime equals I omega y, okay, then what will happen? Then what will happen is that the exact solution is basically e to the power lambda h, right, to the power n times y naught is equal to yn, right? That is the exact solution. That means the exact solution is basically is nothing but has e to the power I omega h. Okay, e to the power I omega h is the is the exact solution. That means yn equals e to the power I omega h times to the power n times y0. Okay, so this is the exact solution, exact analytical solution for this problem. Okay, exact analytical solution, right? I mean, essentially I substitute for lambda equals I omega instead of any real component, right? Real component is equal to 0. So we are looking at purely oscillatory solution. Okay, a purely oscillatory solution. That means our exact solution would look something like this by design, right? This is by design. We have an oscillatory solution. So if I were to draw, that means my exact solution is going to look like, right? It is not growing or not decaying. Let us say it is basically purely oscillatory. Okay, for some time. So this is basically the t. This is your y of t. Okay, that is the exact solution. Now, what will happen if I try to calculate this using the explicit Euler method? Okay, explicit Euler method we want to compute. But before I do that, actually we have already seen this in discussing explicit Euler method. We said explicit Euler method is basically never stable for purely imaginary lambda, right? That's that statement we made before. Why did we make this statement? We said that stability diagram, which is a circle, it is never touching the y-axis, right? So for purely imaginary lambda, that means when you have lambda I, that means if your point is only on the y-axis, because this circle is never touching the y-axis. So any value you take on the purely imaginary lambda, this is always unstable, right? You cannot get whatever value you multiply with h, you can never get this to be inside this thing, right? Because it will always be going on this line only, right? You can never get into this circle because the circle is not touching this thing. Only at x equal to 0, it is passing through x equal to 0, 0, right? Or xy equal to 0, 0. But however, I would like to take a look at this thing. What exactly is explicit Euler method doing? That means we know that sigma equals 1 plus lambda h for the explicit Euler method. That means this is nothing but 1 plus I omega h is the explicit Euler method. That means this is nothing but square root of 1 plus omega square h square times e to the power I theta times e to the power I theta, where theta equals tan inverse imaginary part is omega h divided by real part is 1. Okay, so this is your sigma. We know that now for any value of omega, whether it is positive or negative, omega square is always positive. For any value of delta t which is positive, this is always greater than 1. This is always greater than 1. That's why this is always unstable, right? This is not going to be stable at all. Okay, okay, that is fine. I mean, then you may ask, like, why are we looking at this method? This is anyway unstable. But I want to make something about the phase error. So this is the amplitude error, which is basically growing because the amplitude keeps going. Whereas what about the phase? The phase is dictated by theta, right? That is tan inverse omega h. What is the phase for the exact solution? The phase for the exact solution is e to the power I omega h. That means if you were to take e power I theta, is equal to e to the power I omega h, then the phase is omega h, right? So the phase for exact solution is omega times h. Okay, that means it will be for one step it is going to be omega h. For the next step it is going to be omega h times 2, right? 2 omega h, and it is 3 omega h, and so on, right? That is what is this phase, right? Because this is theta, 2 theta, 3 theta, and so on. Okay. Then what about the phase for the numerical problem? Numerical problem phase is given as here. We have just written it. If I solve it with explicit Euler, I have theta equals tan inverse omega h, right? So instead of e to the power I omega h, I have e to the power I tan inverse omega h, okay, which is basically going to give me, so phase for explicit Euler is nothing but tan inverse omega h. Okay, what is tan inverse theta? So tan inverse x for small values of for small x, tan inverse x can be written as x minus x cubed by 3 plus x power 5 by 5 minus x power 7 by 7, and so on. Okay, so that is the tan inverse x expansion. Then what is the phase error between the exact solution and the explicit Euler solution? That is nothing but omega h minus tan inverse omega h. So that is the phase error, which is nothing but omega h minus, if I substitute for omega h in place of x, we're going to get omega h minus omega cube h cubed by 3 plus omega power 5 h power 5 by 5 minus 7 by 7, and so on. Okay, so this is going to be the leading order term is omega cube h cubed by 3. Okay, so that is the phase error. This is the phase error one for one step. Okay, that means for n steps, the phase error is n times this phase error. Okay, that means n times this omega cube h cubed by 3. Okay, that means that means this is positive. Okay, this is positive. So there is a phase lag when you use the explicit Euler method. There is, of course, the amplitude is growing, so it will be unstable. All these things are fine. But then I want to make a point here. How does it look like? That means if I try to solve this problem using explicit Euler, which is unstable, then my solution is going to look like right. You see, it's kind of grows as you go, and it also there is a phase lag. You know, it kind of goes out of phase. So the amplitude is growing, right? The amplitude is growing like this, but then you see that there is a phase lag. That means this is there, right? So this is the first one is exact solution, which has a phase of omega h, whereas this one has a phase of tan inverse omega h. So that phase keeps growing as you go out. So that is the phase error. Okay, which is involved. So many a times we are interested in knowing this thing, right? If you have a seismic activity or some kind of a spring mass system or something, then it doesn't reach the peak value at the corresponding time. It's going to reach the peak value after a certain time or before certain time. So there are errors not only in terms of amplitude, but there are also errors in terms of phase. That means at what time it's going to reach the bottommost point, or at what time it's going to reach the topmost point, right? These are different. So this is the phase error that is involved, which of course this is not useful in the context of explicit Euler but method, because eventually it is going to diverge. But then it is interesting to note that there is a phase error that is involved, and we're going to apply this concept to implicit Euler method, which is anyway stable. Okay, and then we'll calculate what is the phase error in the implicit Euler method as well for purely imaginary values of lambda. Okay, like what we have done now. Fine. So that is about it. We will continue with the implicit Euler method and then look at the trapezoidal method in the next lecture. Here it is a holiday tomorrow. Tomorrow is a holiday. So 5th November is holiday on account of Guru Nanak Jayanti. So as a result, no class tomorrow. Okay. We're going to directly meet on next Monday, that is on 10th of, so next class is on Monday, 10th of November. Okay. Fine. Any questions, anybody?
Sir, just interest of syllabus, no, sir.
Yeah.
Our syllabus will complete by this month, no, sir.
Month end, I think we have classes up till when is the last instruction day? I think last instruction day is until 12th of December. We'll probably finish by 8, 9, 10 that week, December 8, 9, 10, or even a little earlier, maybe. We'll try.
Okay, sir. Right,
Okay.
sir.
Yeah.
Before will be better, sir, because we have to prepare everything. That is
Correct. Yeah, sure. Yeah, we will try to finish by maybe, that 3rd of December or that week.
Right, sir.
Maybe if required, we can take one extra lecture or something. Okay.
Right, sir.
We will do that. If you want, I can. I think it's okay. We'll try to do maybe an extra lecture if it is required after the first week of December.
Right, sir.
Yeah. Yeah. Okay. Any other questions? I forgot to post your assignment. I'll do it by tomorrow. Okay. Tomorrow you'll have the assignment in with you. Probably I'll give some 1 week to 10 days, which you can submit. So this is 4th, 5th. Okay. So maybe, but then when is your exam? 16th, is it? Okay.
Yes, sir. It is.
Okay. Yeah. We will see. I think you should be able to do it easily with that. Okay.
Okay.
Fine. All right. Any questions, anybody? Okay, if no questions, I'm going to stop here. We will catch up again on Monday. It is 10th of November. Okay. Fine.
Okay, sir.
Okay, thank you, sir.
All right. All
Thank you,
right.
sir.
Yeah. Thank you, everybody. Bye-bye. Part we have, I've given you a simple function that is